Let's talk about the first derivative test. Now, this section is all about the derivatives and the shape of a graph. And this first derivative test is going to help us classify critical values. So this helps us classify critical values. Okay, that's what the purpose of the first derivative test is. And before we discuss this first derivative test, I first want to remind you of a couple of facts. If f is an increasing function at the point x, then what does this mean? This means that the first derivative at x is going to be greater than 0. All right. Similarly, if f is decreasing at x, then that means that the first derivative evaluated at x is going to be less than 0. Okay, cool. So the first derivative test tells us the following. Suppose that f is a continuous function over some interval I containing the critical point c. So remember, we're not saying that the function needs to be differentiable because critical points can be points where the derivative doesn't exist, such as absolute value, right? Or when you have a cusp. So all we need is continuity, all right? If it is differentiable over the interval, except possibly at that point C, so now we really are saying we want it to be differentiable, just not at the critical value, then it satisfies one of the following descriptions. And when I describe the first derivative test to you, I'm really going to describe it to you using pictures. So I want to draw a little line, and then I'll have C as my critical value like this. And let's say that on the left side of C, your function is increasing, and then on the right side of C, your function is decreasing. So when you have this situation, then we have a local maximum, right? I hope this makes sense, right? If the function increases, then you hit your critical value, and then it decreases right after. That means that C was like a local maximum right there. Similarly, if I draw another little line over here, I put my critical value C down, and then it's decreasing on the left of the critical value, and then it increases to the right of the critical value. In this scenario, we have a local minimum. Okay, so these are the first two cases of the first derivative test. We have a third case as well. So I'm going to draw two pictures for this third case. My first picture looks like this. So here's C, and then say it's increasing, it hits C, and then it continues to increase. And then the second picture I have looks like this. Here's C. Let's say it decreases, it hits C, and then it continues to decrease. In either of these situations, we have neither a max nor a min. In other words, this third situation says there is no extrema. Okay, your critical value is just a place where the curve maybe flattens out momentarily and then it continues increasing, or maybe it's decreasing, it flattens out and it continues to decrease. So if I were to draw a couple graphs to illustrate that, this might look like increasing, flattens out, and then increases, or the situation might be it decreases, flattens out, and then decreases. In either case, we have neither a max nor a min. So why don't we take a look at an example? Let's use the first derivative test to find the location of all extrema for f of x equal to x cubed minus 3x squared minus 9x minus 1. So the first thing I want to notice is f is continuous since it's a polynomial. Okay. In fact, once I take the derivative, it'll be obvious that it's continuous. So let me take the derivative here. So the derivative is 3x squared minus 6x minus 9. So this means that f is differentiable everywhere because the derivative exists everywhere. So I really didn't need to mention that it was continuous because differentiability implies continuity, right? Differentiability is stronger than continuity. So what do I want to do next? So the next thing I want to do is I want to find the critical values. So let's find the critical values. And the way that I find these critical values is I'm going to set the first derivative equal to 0. So why don't we put 0 is equal to 3 times c squared minus 6 times c minus 9. So I just decided to call my critical values c. And I can factor out the greatest common factor. So that's going to be a 3. I'm going to factor out the 3. I'm going to get c squared minus 2c minus 3, like this. And that further factors as 3 times c minus 3, c plus 1. Okay, so this tells me that my critical values are going to be c equal to 3 and c equal to -1. So I have 2 critical values. And you can see I put a 1 here because that's like the first step of my process. So the second thing I'm going to do, put a 2 here, I'm going to classify the critical values. Okay, so let's take a look at how we're going to do that. So what I'm going to do here is I am going to create a little number line. So let's put a little number line over here like this. And I'm going to put my critical values in the proper order. So -1 is on the left because it's smaller than 3, and 3 is on the right, like this. And then the method that I'm going to use is I'm going to use test points. So there's different methods on how to classify these critical values, how to figure out the intervals of increase and decrease. But in this case, I'm going to use test points. So I am going to pick a value that's less than -1. So I'll take -2, and I'm going to evaluate f prime of -2. Okay. I know that the only places that my derivative is going to change sign is -1 and 3. So it really doesn't matter what value I pick as long as it's less than -1. I'm just going to pick -2. My test point for the middle section, I love using the number 0. So I'm going to calculate what f prime of 0 is. Because 0 is an easy number to work with, right? And then for my value to the right of 3, I'm going to calculate what f prime of 4 is. And let's look at the signs of each of those things. So when I calculate each of these numbers, let's put our calculations at the bottom over here. We get f prime of -2. What is that going to be equal to? That's going to be equal to 3 times -2 squared minus 6 times -2 minus 9. When we evaluate this, we're going to get 15. Okay. When I calculate f of prime of 0, f prime of 0, plugging in a 0, the first term is 0, the second term is going to be 0 in the derivative. So we just get -9 remaining. And then for the last guy, we're going to have f prime of 4. F prime of 4 is going to be equal to 3 times 4 squared minus 6 times 4 minus 9. When you evaluate that, we're going to get 15 yet again. So remember at the beginning of this video, we said that positive numbers meant that the function was increasing, negative numbers means the function's decreasing, and positive means that the function's increasing. So I'm going to change my marker back to blue, and we can see that our function increases up to -1, between -1 and 3, it decreases, and then to the right of 3, it increases. So what's our conclusion? Our conclusion is that we have a local max at x equal to -1, and we have a local min at x equal to 3. And if you wanted to find the actual points, we would substitute in the x value to find the y value to get the location, the precise location of our point. All right, everyone. We'll work on some more examples in class when we meet in person later. I am going to show you a method that uses a table instead of using test points, but we will continue this in the future. Take care, everyone.